In this last example, we'll take a look at a trig function. So let's say f of x is 1 over sine x cosine x. And we'll restrict our domain so that 0 is less than or equal to x less than or equal to 2 pi. So is this function even defined on this whole domain? Actually, we run into problems, right? If sine is 0 or cosine is 0. So if I look at either endpoints, 0, sine of 0 is 0, sine of pi is 0, sine of 2 pi is 0. On the other hand, cosine of pi over 2 is 0, and cosine of 3 pi over 2 is 0. So the function is not even defined on this whole domain. This is what we want to graph this region. So technically, our domain would be 0 to pi over 2, pi over 2 to pi, pi to 3 pi over 2, and then 3 pi over 2 to 2 pi. So our domain has a lot of breaks in it. We're going to have discontinuities at pi over 2, at pi, at 3 pi over 2, and then even at our endpoints we have discontinuities. So those will play a role in graphing our function. All right, so we've determined what the true domain is here. We're still going to sketch the graph between 0 and 2 pi. First things first, let's compute f prime. And as I said, I'm going to kind of skip through the gory details. But if I compute the derivative, this is ends up being sine squared minus cosine squared. All divided by sine cosine quantity squared. And that's perfectly good, though I'm going to use some trig identities to help kind of clean things up here. This sine squared minus cosine squared, that should seem familiar to you from your investigation of trig functions. And let's remember that are double angle identities. So for instance, that cosine of 2 times an angle is the same as cosine squared of that angle minus sine squared of that angle. And the other versions of this, we can use Pythagorean's identity to say this is the same as 2 cosine squared a minus 1, and that's the same as, or 1 minus 2 sine squared of that angle. So these are 3 different versions of the double angle for sine, and we've got a double angle for sine, or cosine, sorry, and we've got a double angle for sine. That sine of twice an angle is just 2 times sine of the angle times cosine of the angle. All right, so those will be useful to us in cleaning things up. And so let's just kind of squirrel this away. Useful information. But the first place I'm going to use it is right here, and the fact that, well, I don't have cosine squared minus sine squared. I have the opposite of it, the negative of it. So I can replace it with negative cosine 2x. So this is negative cosine 2x. Now this is not necessary to clean this up. because I know where we're going, this is going to make our lives a little bit easier. My goodness, my handwriting. So sine x cosine x quantity squared. Makes it a little bit easier to find where my zeros are. I can look at this and see, solve for when cosine of 2x is 0, which I'm going to need for my critical values. Before I get there, let's compute the second derivative. So if I do f double prime of x, and again, I'm going to skip the details, but I do have a quotient rule, so I end up with a monster on top. So this is 2 sine of 2x times the quantity sine of x cosine x quantity squared plus cosine 2x times 2 sine x cosine x times cosine 2x again, all divided by sine x cosine x to the fourth. So most of this is just straight quotient rule, derivative of the top times derivative of the bottom, derivative of the top times bottom, whatever. So this cosine 2x, well, when we take the derivative of the bottom, we get a cosine squared minus sine squared again. So that's where that came from when you're working this out by hand. Let's clean this up a bit as well. So I've got a sine cosine here and a sine cosine there. So I can factor those out and cancel, leaving me at the bottom with a power of 3. And then a little bit more cleanup. I've got a 2 times a sine cosine, which is exactly what my double angle formula tells me here. So the top cleans up a little bit. So this is equal to, what is this, sine squared of 2x. And then over here, I'm going to have a plus 2 cosine squared of 2x all over sine x cosine x quantity cubed. And one little last bit of housekeeping to make this a little bit cleaner. We know that sine squared plus cosine squared is 1. So this ends up being 1 plus cosine squared of 2x, all divided by sine x cosine x quantity cubed. So this form will help me, again, see how to deal with the sine graph, which let's get on that. So first things first, let's do the sine graph for f prime. So f prime, we're going to be going from 0 to 2 pi. So this is f prime from 0 to 2 pi. And let's investigate. Where is this 0? Well, it's 0 when cosine of 2x is 0. Well, that's going to happen when the interior, the input, is either pi over 2 or 3 pi over 2, which tells me, well, okay, I have to mark this off. So let's see where pi is. Pi's here, and pi over 2 is here. 3 pi over 2 is here. Now that's where the denominator is 0, so those are critical values. It's undefined there. And then the top is going to be undefined at pi over 4, because if I put pi over 4 in this, it's cosine of pi over 2. At 3 pi over 4, because when I put that in for x, that'll be cosine of 3 pi over 2. At 5 pi over 4, because when I put that in, that's going to be 5 pi over 2. And then finally 7 pi over 4. So when I put that in for x here, that'll be cosine of 7 pi over 2, another 0. So those are my zeros. Pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. And then my places where it's undefined will be pi over 2, pi, 3 pi over 2. Now, I need to go through and evaluate, determine the signs of this. That's a lot of points, so I'm going to skip the gory detail. Again, you should be picking values between 0 and pi over 4, say pi over 6, or between pi over 4 and pi over 2, say at pi over 3, and continue through, put them in to your function, determine is it positive, is it negative, but I've done this already, so I know that it's negative. Oops. Negative here, positive, positive, negative, negative, positive, positive, and negative. So we can see that it's increasing from 0 to pi over 2, or sorry, decreasing, increasing from pi over 4 to 3 pi over 4, then decreasing on to 5 pi over 4, then it'll be increasing again to 7 pi over 4, and then decreasing for the last leg of it. Okay, that's the sign graph for f prime. How about the sign graph for f double prime? So f double prime, its sign graph going from 0 to 2 pi. Well, let's take a look at this function. So it's nice that I cleaned it up. This is 1 plus cosine squared. Notice cosine squared is always positive, so the top's always bigger than 1. The numerator can never be 0. So the only place where we get sign changes is when the denominator is 0, and we've already figured that out. That's going to be at pi, pi over 2, and 3 pi over 2. And so then building the sign graph for this, again, take values, plug them in, but it'll be positive in this region, negative, positive, and negative. Right? So we know that it's concave down up here, concave down here, concave up, and concave down. Probably should have done the same here. Increasing, increasing, then we would have decreasing, decreasing, and decreasing. So we know the general behavior of my graph, increasing, decreasing, all that business, concavity. So I should be taking limits now, and I encourage you to attempt all these limits. However, there are a lot of limits. I would have to figure out what's going on at pi over 2, at pi, 3 pi over 2, even at 0 and 2 pi. So that'd be 1, 2, 3, 4, 5 limits. But then I'm going to get a double up because I'm going to do left and right limits here, left and right limits here, left and right limits there. So I would get 8 limits to compute. I encourage you, compute those limits. Compute the limit as x approaches 0 from the left of 1 over sine x cosine x. You will find that if you did that, this would be positive infinity. Do it again for the left and right limits of pi over 2, for pi, for 3 pi over 2, for 2 pi. Work them out. Make sure that you understand how to argue these through and determine what their limits have to be. However, because of the sake of time, I want to honor your time. I don't want you to have to sit here and listen to me talk for so long. We're going to find that actually the graph will force our hand, and we'll be able to see what those limits have to be. So let's put everything together. I claim that we've got enough to determine the shape of this graph. So I'm going to graph, here's the y-axis, here's the x-axis. I'm only going to 2 pi. Key values, pi, pi over 2, 3 pi over 2, pi over 4, 3 pi over 4, 5 pi over 4, having fun yet? 7 pi over 4. Okay, now let's get our information here. It is going to be increasing when? Well, it's going to increase from pi over 4 to 3 pi over 4. Then again from 5 pi over 4 to 7 pi over 4. So from here to here, will be increasing. And then again from 5 pi over 4 to 7 pi over 4, try to say that 10 times fast, it's increasing. On the rest of the point, it's decreasing. So it's going to be decreasing from here, decreasing in here, and then decreasing in this last little bit. Okay, that's the behavior there. How about concavity? Well, it's going to be concave up from 0 to pi over 2. So let's, from 0 to pi over 2, it's concave up. From pi to 3 pi over 2, it's also concave up. So from here to here, concave up. But then it's going to be concave down from here to here, concave down, and then be concave down from there to there. All right, so we've kind of labeled this well, I hope. You can read this. I know I've got discontinuities. Those are going to turn out to be asymptotes at 0, at pi over 2, pi, 3 pi over 2, and 2 pi. Those are my asymptotes. And at these critical values, pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, at those critical values, we know we're going to have a min at pi over 4, a max at 3 pi over 4, a min, and a max. So let's evaluate what those numbers have to be. So let's build a little table over here. So I've got my x and my f and pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. We put this into our function, sine, cosine. At pi over 4, this is root 2 over 2. Cosine's root 2 over 2. So that's 2 over 4, also known as positive 2. Do the same thing. Put 3 pi over 4 and we get negative 2. Put 5 pi over 4, we get positive 2. Put 7 pi over 4, we get negative 2. So what do we know? We know at pi over 4, so let's say that this is 2, and maybe this is negative 2. So pi over 4, we have a min at that point. At here, I guess I should make my negative 2 a little bit lower, negative 2. We have a max here. And then we're going to have another min at 5 pi over 4 and another max here. And you may be wondering, how can I have a min at 2 and a max at negative 2? Well, it's because of all these discontinuities. And what's the rest of the business? Well, as I said, I actually don't even need to compute these limits because the graph, the information tells me everything. It's got to be decreasing down to this point and increase up. And it's got to stay concave up the entire time. So it has to look kind of parabolic like that. Similarly here, I'm going to have to increase up to this point, then decrease after that, and continue to stay concave down. So it has to look like this. Here, decrease, then increase. It's got to look like that. Increase, decrease, and it's going to have to look like that. And so now, since I graphed it, I don't even have to go through the arguments. I can tell you, oh, the limit as x approaches pi over 2 from the left, oh, it's positive infinity. The limit as x approaches pi over 2 from the right, oh, it's negative infinity. The decreasing and increasing and concavity tell me this is exactly what it has to do. Since I know it's going to plus or minus infinity, and the details here should tell me that it's got to be going to infinity here, infinity, infinity, negative infinity down here. And this is the graph of y equals 1 over sine x cosine x. Hope that helps. Hopefully this example brought back some fond memories of trigonometry. Those of you going on to Calc 2, trigonometry is a key that unlocks so many doors. So don't think that it's going away anytime soon. So do be sure that you know your double angle identities. These are so useful and will come up quite often. Well, that wraps up this section. Best of luck with your studies and happy mathing.